today we are going to discuss about a very good chapter, that is dual nature of matter and radiation. In this chapter, according to the name, we will talk about the dual nature of matter and radiation. So if we talk about any radiation, we also can say that radiation as light. So light has two types of nature, as there is written as dual. So dual means there are two types of nature. First is wave nature and the second is particle nature. Similarly, in the case of matter, we have two types of character. One is wave character and second is particle character. So, in the case of light, we will talk about the wave nature in class 12 by the diffraction experiment, by interference experiment. And in the case of matter, any matter, we will talk about wave nature by Davisson and German experiment. In the case of particle nature of light, this character is proved by the Albert Einstein in 1900, and this experiment is known as photoelectric effect, which proves that light has particle nature. So let's talk about more about the photoelectric effect. What kind of experiment he has done to prove light has particle character? Okay. So in 1900, Einstein performed an experiment. In this experiment, he taken a metal surface, and in this metal surface, Einstein fall a radiation of high frequency, and Einstein observed that there are electrons that are emits out from these metal surface. As in any metal, there are free electrons on the surface, and when this radiation of high frequency, or we can say that high energy, falls on the metal surface, this emits out the electrons from the metal surface, and this experiment is known as photoelectric effect, and these electrons are known as photoelectrons. And this can only be happen if and only if the light has particle character. And Einstein said these particles as photons. So let's talk about photons, because in this chapter, if we don't know about the photons, the complete study is not going to happen. So let's talk about photons. As I said, light is made up of particles, and that particles is known as photons. So photons have certain properties that we have to study. So with the help of Newtonian mechanics, we cannot determine the mass of the photon. The first thing that Einstein said, that by Newtonian mechanics we cannot find the mass of the photon, but we can say that the rest mass of photon is 0. The second thing is that each photons travels with speed of light, that is 3 into 10 to the power 8 meter per second. The third thing about the photon is each photon has certain amount of energy and momentum, and this energy and momentum is given by E is equals to h nu, or we can say that E barabar hc by lambda, or for momentum P we have a formula h by lambda, and these formulas are fixed for the photons, and that energy will be totally depends upon the wavelength or frequency of any radiation, and that momentum is depends upon the wavelength. Then again, the point number 4. Before moving the point number 4, from here we can see that momentum is related to wavelength, and this gives proof that light has dual nature and radiation has dual nature, because as momentum, if anything has momentum, this is the particle quantity. But if we talk about wavelength, this is the wave quantity. Okay, so let's move forward. Point number 4 is that if any photon collides, photon collision is perfectly elastic. What does it mean? It means that the momentum of photon is always conserved and kinetic energy of photon is always conserved. Okay. And next thing is that if intensity of light is increased, number of photons also increased, but energy remains same for each photon. What does it mean? If we have two bulbs, one is of 50 watt and another bulb of 100 watt. This bulb has low intensity, but this bulb has high intensity as compared to this bulb. So let this bulb given out 5 photons, but this bulb given 8 photons. But the energy of each photon is always h nu. Energy of each photon is always h nu. That means if we take 2 photons in a plate, then we cannot differentiate according to the energy. Okay. So this is all about the photons. Let's move forward and talk about the emission of electron from the metal surface. So as we all know, if we talk about the emission of electron from the metal surface, So we only talk about the emission of free electrons. Emission of free electrons that are free to move, right? So electrons at the surface of any metal are less bounded as compared to electrons in the bulk, right? So these electrons are named as free electrons. Okay, so these electrons are known as free electrons because they are less bounded as compared to the electron present at the bulk. Okay, so we know about the free electrons, what electrons are called free electrons. Let's move forward. If we talk about the emission of electrons from the metal surface, what we actually need is energy. What we actually need is energy, because in any type of emission, either it is thermionic emission, either it is electric emission, or it is photo emission, we are supplying energy to emit electron. Like in thermionic emission, we supply heat. Secondly, in electric emission, we apply electric field, that is, we apply electrical energy. And thirdly, in photo emission, we are supplying light energy for the emission of electrons, and this effect is known as photoelectric effect, as we already read about the photoelectric. Okay, so we need energy to emit electrons. Okay. So we have a minimum amount of energy required to emit any of the electrons from the metal surface, and this minimum amount of energy is called work function of any metal. As we said, for any type of emission, we need energy, and the minimum amount of energy to emit an electron is the work function of that metal surface. Work function is a type of energy, and it is measured in electron volts. And we know 1 electron volts is equals to 1.6 into 10 to the power minus 19 joule. Okay. So different surfaces have different work function. That is, for different surface, like for cesium metal, we have different work function. For any iron sheet, we have different work function to emit the electron from the metal surface. But if we supply the minimum amount of energy, the energy that is equal to the work function of the metal surface, but this is not always true that we supply the energy and we will get the electrons out of the surface. This is not always true, because when we supply energy, these electrons are also colliding with other electrons, so it is possible that some extra amount of energy we need, because some energy is lost due to collision of the electrons, right? So that is not always true that if we supply a minimum amount of energy, that is equal to work function, and we will get the electron emit out from the surface. That is not always true. Okay. And we also cannot see that if we supply the energy greater than the work function, by a full possibility that the electron emits out from the surface, we also cannot see that. So we can see that if we supply the energy greater than or equal to the work function to any metal surface, the electron may come out. Okay, the electron may come out. electrons may come out. Okay. When we say that the electrons 100% comes out, is that when we say that if we incident a certain amount of energy that is greater than the work function or equal to the work function of the metal surface, and these electrons makes best use of the incident energy, then we can 100% say that electron emit out. But if the electron do not use it as best, they supply the energy, they lose energy in the form of collision, then we cannot say that. We always use may in the place of can. Okay, let's move forward. Let us suppose that we incident a energy that is equal to h nu, and the electron comes out from the metal surface. Then this energy E is equals to the work function plus, because the minimum amount of energy required to emit the electron from the metal surface, this plus when electron comes out, then the extra amount of energy turns to its kinetic energy, and this kinetic energy is the maximum kinetic energy. Okay, so we can write it as maximum kinetic energy is equals to E minus phi, and we can write in the place of E as h nu minus phi, and this equation is called as Einstein photoelectric equation. This equation is called as Einstein photoelectric equation. Okay. Okay, let's move forward. So we have the kinetic energy is equal to h nu minus phi. As we have seen that we need a minimum amount of energy. We need minimum amount of energy, and this energy is equals to greater than equal to the work function of any metal. So we can write this energy as h nu, where nu is the frequency, and this is greater than equal to phi, and we can write this as minimum, because energy is minimum, so frequency is minimum, because this is constant. Then what we can write, nu minimum is greater than equal to phi by h, right? And what we can say that the minimum amount of frequency we need is phi by h, and we called it as nu naught, and this is the minimum amount of frequency we need to emit an electron from the metal surface, and this frequency is known as threshold frequency. This frequency is known as threshold frequency. I repeat, the minimum amount of frequency need to emit an photoelectrons from the metal surface is called threshold frequency. It's called threshold frequency, and it is denoted by nu naught and is equals to phi by h. So we need this amount of frequency of radiation to emit the photoelectrons from the metal surface. So we can say that the frequency nu must be always greater than equal to nu naught. This minimum frequency, okay, this minimum frequency is called threshold frequency. If we put in this equation that we have h nu minus phi and in place of phi we can write h nu naught, because nu naught is equals to phi by h, then phi is equals to h nu naught. Okay, so kinetic energy maximum is equals to h nu minus h nu naught. Okay, so if we talk about the frequency, then we also talk about the wavelength, because a wavelength is equals to c by nu. If we needed the minimum amount of frequency to remove electrons from the metal surface, then we need it as maximum. So if we talk about the maximum wavelength of light that emits the photoelectron from the metal surface, and this wavelength is known as threshold wavelength. And we can denote this threshold wavelength as lambda naught, and this is called as threshold wavelength. So in this equation we also can write this equation as kinetic energy max is equals to h nu minus h, in the place of nu we can write c upon lambda, and in place of this we can write c upon lambda naught. Okay, so we have two equations. One is kinetic energy max is equals to h nu minus h nu naught, and other is hc upon lambda minus hc upon lambda naught. If we plot a graph, for by using this equation, what equation? The kinetic energy max is equals to h nu minus h nu naught, and we can compare this equation with the equation of a straight line, and the equation of a straight line is y is equals to mx plus c. From here we can see that the slope is equals to h, and in the place of x we can use nu, that is frequency, and in the place of y we are using kinetic energy. So if we plot a graph, what we get? We have an intercept c, that is minus h nu naught. So if we plot a graph, we will get a straight line whose intercept is negative, and this intercept is equals to h nu naught, and this is the graph between the kinetic energy and frequency, and this is the minimum amount of frequency, that is nu naught. Okay, similarly, if we plot a graph for the equation hc upon lambda minus hc upon lambda naught, in this case if we compare this equation by the equation of a straight line, what we get? We get a graph between the kinetic energy and maximum kinetic energy and 1 upon lambda, and this is also a straight line. Here the intercept is hc upon lambda naught, and this is equals to 1 upon lambda naught. Okay, this is the graph. If we use this equation, we can plot the graph according to this, and we can see that this is the maximum, this is the minimum 1 upon lambda naught value. So if we reciprocate it, so this is the maximum wavelength for the any photoelectric emission.